We have a line integral to evaluate over a curve that is a circle. Happens to be a circle centered at 2, 3 with a radius of 2. And so the first thing we notice is that the curve is a closed curve, by the way they describe it, which we assume is the entire circle. So it's closed, and after we check for whether or not it's closed, we do a quick check for independence of path. So we answer the question closed, yes, and then independent of path. Let's check that. If this answer is also yes, then we're done. The answer is 0. What's the check for independence of path? Well, the function that's multiplied by dx, we call that p. The function that's multiplied by dy, we call that q. We check the x partial on q and see if it's equal to the y partial on p. For us, the x partial on q is 2. The y partial on p is 6. So no, not independent of path. But you are closed. And so when you're closed and you aren't independent of path, you could parameterize this path. You definitely could always do that. But we have another way. So we could parameterize the path and just perform the line integral over that path. We're going to find that that is going to be the way we don't want to go. We're going to employ Green's theorem so long as all the conditions are satisfied. And so Green's theorem says, well, as long as the functions p and q and their partials are all continuous in the interior of the region, then what you can do is if you are closed, simple, piecewise and smooth, and counterclockwise, you can trade the line integral in for a double integral over the interior region, where the integrand to that double integral is qx minus py. Okay, not a total necessity, but let's go ahead and plot this here. We have the point center is 2, 3, and the radius is 2, and so two, 3 is the center, and the radius is 2. So this circle, let's try this out. Okay, circle's going to look something like that. We could parameterize that. It's going to be hard. We could. But instead we're going to use Green's theorem, and the interior region, R, that we're discussing is that. So the curve C, let me just denote it here. The curve C, counterclockwise notation, orientation, and the interior is R. Okay, but notice qx is 2, right? We found that. Py was 6. Qx minus py is a constant. It's a negative 4. And so we can pull that constant out, and we're looking at negative 4 with the integrand now being a 1. We just have to recognize that as the area of the region, R. But it's a circle of radius 2. So the area of that region is pi r squared, which is going to be 4 pi. Radius is 2. It's a circle. Pi r squared is the area. So we get 4 pi for that. So then we can answer the question and say that the value of that line integral is going to be negative 16 pi. And yeah, that's your answer.